What I'd like to talk about today is some things about planet formation, and I want to say a little bit about what we know about planet formation. Focus on some of the problems that are open and things we don't know, which I think may be more things than you think, given that it's an old problem that people have studied for a long time. And also say a little bit, of course, about the work we're doing at CCA to try to find out more about those open issues. So I'm happy to take questions during the talk. So if in the room people want to ask questions, just do so, and remember to turn your microphones on so that people on Zoom can hear. So I want to begin by just saying a little bit about, if you like, what we would like to know about planet formation. What is the goal of studying this area? And I think from a sort of solar system perspective, like an old-fashioned perhaps solar system perspective, the idea of where the Earth came from, how the Earth formed, sort of fits as the middle chapter of a sort of trilogy of movies of thinking on the really big scales. How did galaxies form? How did stars form? How did structure form in the universe? Then how did we form the Earth? And then eventually, how do we go on from that to the origin of life? So if we just sort of think on that big picture, very big picture view of things, I would sort of characterize it that most aspects of how the Earth formed are sort of understood at the level that would be in like an undergraduate physics or astronomy textbook. And as I'll emphasize, it is actually a case of most of them, and there are still things that are sort of fairly basic, which are really up for grabs in terms of how the Earth formed. But then if we sort of come to a more modern perspective, perhaps, with the discovery of extrasolar planets, so the first of those was 25 years ago, roughly, it's a bit more than that now. One of the immediate questions that was raised by observations of extrasolar planetary systems was, is the solar system a typical planetary system? And that originally came about back in sort of 1995 because the first exoplanets that were found, partly for observational reasons, looked completely different from the solar system. So it immediately raised the question, well, how does the solar system fit in there? And 25 years of observations later, we know the answer to that question. The solar system is not a typical example of a planetary system, because if we look at a random star, we find that those stars have pretty massive planets, Earth mass or bigger, in close-in orbits that are well inside where Mercury is in the solar system. So if we just sort of picked a star at random, it wouldn't actually look like the solar system. It would not look like the solar system, our solar system, yeah. So we know that, so that part is sort of determined, but the part that's still open is whether, if you like, the solar system is, just a little bit different from one of those planetary systems, or whether it's really a sort of more rare kind of outcome of the process. And that question is interesting, and it's also hard to define.
Yeah, just a quick question about that previous statement. Do we feel that we have a broad enough, truly random sample, uniformly distributed over the various kinds of solar systems to answer the question as definitively as you've answered it?
Yeah, so the question is, do we have a good sample for that?
Across all kinds of, yeah.
So it depends exactly what you mean. So if we think about stars in the solar neighborhood, right? So relatively speaking, in our region of the galaxy, I mean, not really close to us, but in our region of the galaxy, NASA's Kepler satellite stared at basically a blank, a random patch of sky and monitored all the stars in that region. So if we think about stars that are sort of the same mass as the sun and lower, and in our region of the galaxy, the answer is yes, we have a good sample.
I guess what I'm at, I don't know exactly how evolved the art of detecting extraplanetary solar system, is. So can we in fact say that we can detect Earth-like planets at roughly Earth-like orbits for stars that are considerably far away from us? With the probability we're comfortable
so it depends on how far away the planets are from the star and also the type of star. But if it's a star sort of like the sun and the planets are, let's say, Earth distance from the sun or closer, then we have the technology is good enough for that. If you go further out, the answer is everything is open. Yeah. But we are restricted to our region of the galaxy. So and the stars in the galaxy have different properties in different places. So if you went very close to the galactic center, for example, it'd be a different story, and observationally, you wouldn't be able to say anything. So yeah, so are we a bit atypical, or are we really rare? And so there's a sort of question of definition, because all planetary systems and all planets are going to be a bit individual in their own way. And so you have to ask, well, which aspects of being similar or different are the things you care about? And a lot of people care about whether planets are habitable, and maybe eventually looking for evidence of life in the atmospheres of planets. So an important metric is, are the characteristics that make the Earth habitable shared by many other planets around stars or not? And that aspect observationally, remains unclear. So maybe that's a bit abstract. So I'd like to begin by just sort of giving an example of one property of a planetary system that we're interested in, and well, how do we sort of understand it? And the question is, how did we get water on the Earth? Okay. And so water is obviously very important for habitability. It's the sort of one of the basic things people agree about as being important. And there's just one piece of sort of physics or chemistry that we have to think about here, which is that if we go to low pressure environments, the stable phases of water is not liquid water, it's ice or water vapor. It's solid or gas. And in the environments in which planets form, which I'll discuss in a little bit later, I'll just tell you that the temperature which separates solid ice from water vapor is about 150 K or 170 K or something like that. It's really pretty cold. So if you think about that, you can make a sort of simple prediction. If you imagine a planet like the Earth, so basically a solid planet, and it's forming from sort of material in its orbit at some distance from the star, its composition should be quite closely tied to what the temperature of that material is. So if you're below this 150 K boundary, then most of the oxygen that we have sort of present in that environment will end up in water ice or in hydrated minerals of some kind, and those will all be assembled into the planet as it grows. And because oxygen is a common element in the universe, that's a lot of water. And so you end up then with a prediction that half or 2/3 of the planet by mass should be made of water. So it'd be sort of a water world. And if you think about the outer solar system and look at an object like Pluto, which is sort of a small solid object far out there, indeed it's got a lot of ice in it. Okay. And if that object was somehow transported to the inner solar system, then on the surface that would be liquid water, and it would be some enormously deep ocean. On the other hand, if you're above that temperature of 150 K, the water will just be in the gas phase. It will just keep flowing in towards the star. It will be lost. It won't be accumulated in the planet, and the planet will be dry. Now, convert that to how things go for the Earth. You need to know, well, what is the temperature where we are in the solar system before the Earth formed, and there was just gas and dust in orbit around the sun at that time. But that temperature would still be set by the same sort of physics as sets the temperature on Earth today, the strength of sunlight at some early stage in the sun's evolution. So it would be, roughly speaking, the same as it is today, 300 Kelvin. So we would say that the Earth is well inside the snow line. We're in this sort of dry region of the planetary system. So the prediction would obviously be that the Earth should be dry, and obviously that is not the case. The most thing we know about the Earth is that it's covered with water. So this is an immediate failure of like a very simple theoretical prediction. So if we just really think about the Earth, we know the answer to this conundrum, but it's taken planetary scientists decades of work to really figure it out. And the key is that you can measure another property of the water on the Earth beyond the fact of just how much of it we have. And that is the ratio of deuterium, heavy hydrogen, to regular hydrogen. So you can measure that deuterium to hydrogen ratio in water on the Earth and compare it to reservoirs in the solar system, which you can also measure by various means. And it's found that that D to H ratio is not a good match for comets. So if you sort of pose this question and you hadn't thought about it, the sort of obvious answer is, well, the water on the Earth comes from comets, because we know that those are like icy objects that occasionally would hit the Earth, but they don't actually have the right D to H ratio. So it's a better match for asteroids in the outer region of the asteroid belt. So the general expectation, the general thought, is that the relatively modest water fraction we have on the Earth came ultimately from sort of the outer region of the asteroid belt, And at some point, those asteroids were transported, scattered into the inner solar system. They hit the Earth, perhaps at a late time, and contributed the Earth's water reservoir. So that's probably what happened for the Earth. So that's a story that planetary scientists have worked out that has sort of lessons, I think, for when we think about extrasolar planets, where we can't observe them in anything like the same amount of detail as we can in the solar system. So one lesson is that we have to think about planetary systems, not planets in isolation, because once you get beyond the most basic properties of a planet, like its mass, the more complicated properties are very closely interlinked with what else is going on in the planetary system where you're considering that planet. Another issue is that the most basic things about habitability for the Earth, at least in this case of the Earth in the solar system, are actually sort of quite subtle and non-obvious, right? So it's not just the case of how far you are from the star determines what sort of water content you would have for the planet. And then if you don't know how a planetary system forms, you don't know about asteroid belts and Jupiters and Saturns and things like that, it's actually quite hard to make even a reasonable guess about what the composition, what the atmosphere, ultimately what the habitability of a planet would look like. Okay, so there's some sort of cautionary lessons from this basic piece of solar system physics.
Phil, can I ask a question about the other axis in your phase diagram for water, which was the pressure axis? It sounds like if we didn't have a high pressure atmosphere, then all of this water that came in from asteroids would have just evaporated anyway. Do we know where the distribution of planets out there lie in terms of the sort of pressure of gases, and whether that's enough to hold liquid water in the liquid state?
Yeah, so that's also a deep and complicated question, right? And so generally we think that many planets would have sort of two types of atmospheres. So there would be a primordial atmosphere, which was perhaps gathered from the gas and dust when the planet was forming, which in many cases is going to be lost. And then a subsequent atmosphere forms by outgassing from the interior. So probably it's that secondary atmosphere we have on the Earth. And so as long as we have enough water-bearing material that forms the Earth, that will eventually be expelled into the atmosphere and potentially, give us something. I think the greater danger is sort of on the other end, that it's like very easy to have a much heavier atmosphere than the Earth. And then, even though the temperature at the surface may be quite suitable for life, the temperature at the surface of the planet is much higher. Yeah. Okay, so let's say a little bit now about what we do know about planet formation, some basic things. And so one thing we know is the environment, and we know that really from reasonably direct observations, as direct as we sort of have in astronomy. So what we have here is an image, a composite image of a young protoplanetary disk, so a disk of gas and dust orbiting a young star. And we've got sort of two sets of images here. These sort of orange rings here are emission in short wavelength radio waves, sort of millimeter wavelength, which trace the distribution of dust around that star. So you can sort of see its disk-like morphology with also these rings here present in this system. And then there's a background image which is taken in different wavelengths, which is this blue colors, which is actually showing a jet of material which is being launched from near the vicinity of the star, and which I'm not going to say more about in the context of this talk, though it's obviously very interesting, and it's related perhaps to the sorts of jets we see from black holes in completely different astrophysical systems. So we can actually observe these things quite well, and so we know quite a lot about their physical properties. So they have scales that are sort of similar to the solar system or larger. The temperature is obviously hot, close to the star, 1,000 degrees Kelvin. Gets down to maybe 20 Kelvin if you go really far out. The densities are what we describe as high in astrophysical terms, but a very good vacuum in sort of more terrestrial terms. And the masses are a small fraction typically of the mass of the star, 10% down to 0.1%, as I've written it on this slide. And the material is mostly hydrogen and helium gas. It also contains other molecules, which are actually what we typically observe when we observe molecules. So we observe things like carbon monoxide. And then the solid material, which is initially in the form of dust. And that might be made up of silicates, ices, various other sort of common materials. And we know that the lifetime of these disks is pretty short by astronomical timescales. It's a few million years, so it's 0.1% or less of the lifetime of a star. So we see these planet-forming disks only around very young stars. So that's the environment. And we also have a sort of general picture of how planets grow there, which is a bottom-up picture of planet formation. So you start with very small dust particles, microns in size. Those collide with each other by various processes. So Brownian motion is one, but then there are others. They collide and stick, and then the larger aggregates stick to even larger aggregates, and the whole thing builds up this way. And you're seeing a movie of simulations that were not done here. They're done by a Japanese group showing how those aggregates build up. And it's pretty well established, both from those kind of calculations and also from lab experiments in microgravity, that kind of direct sticking process builds you up to things that are maybe millimeters or centimeters in size. So you get to sort of small macroscopic dimensions just by things hitting each other and sticking. So from that size, the next step is to build sort of the first objects that look like, I don't know, small asteroids or comets. And those are described as planetesimals. And the image that you're seeing here is an object far out in the solar system that was visited by the New Horizons spacecraft a few years ago, which may be one of the remnants of those planetesimals that we can still see in the solar system. So those are things that are kilometers or maybe larger in size. And from there on in, there's sort of a two-track way of making the different kinds of planets. If we think about planets like the Earth, so basically solid planets, the idea is that the planetesimals collide with each other now under gravity. So not just sort of random collisions, but pulled together by gravity. They collide and grow bigger. And then maybe also the growing objects sweep up some of the pebble-sized stuff that was left over that didn't form planetesimals. And one way or another, that process continues until you end up with something like the Earth. If you do the same thing, maybe further out in the planetary system, and you get to something that's much bigger than the Earth, maybe 3 or 5 times the mass of the Earth, then the gravity of that planet is large enough to really pull in a large amount of gas from the surrounding disk. So at that point, you don't just have sort of an atmosphere around the planet, you have really a thick envelope. And if that goes far enough, you end up with something like Saturn or Jupiter, which is really dominated by gas and only has a relatively small solid content. So that's this sort of overall picture. And at the level of description I've just put on this slide, everything here is thought to be a pretty secure understanding of what happens. So that's what we think we know. Why is it difficult to learn more, to have more details about how this process takes place? Well, the main thing is that although we have a huge amount of observational data, it's really sort of quite restricted in the parameter space that it occupies. So on this sort of here, I've sort of schematically sketched time on the x-axis and then the size of things that we can see on the vertical axis. So when we look at protoplanetary disks, we're looking at young systems, a few million years old. So that's a very small time fraction of the lifetime of a star. And directly, we can observe small dust particles up to things that are maybe millimeters or centimeters in size. So those things are, have a good observational grounding, but it's only in that corner of the parameter space. We can also see, lots of extrasolar planetary systems, thousands of them now. And what you're seeing here is a compilation of the multiple planetary systems that were found by NASA's Kepler satellite. And there's hundreds of those. But those are mostly around stars that are old, billions of years old, so sort of similar to the sun. And the planets themselves are, in some cases, a little bit smaller than the Earth, but not much smaller. So they're sort of the size of the Earth up to the size of Jupiter, or a bit larger than the size of Jupiter. So that's the late large part of the axis. And in the middle, all the scales and time scales in the middle are sort of practically very difficult to observe. And that's particularly the case for sort of intermediate sized bodies that maybe are 100 kilometers in size. If you ask how would you see a 100-kilometer object around another star, or even a population of those objects, that's really well out of reach for anything we can do. So that's that's why we need theory, right? Well, we can't just observe the process. So that's good, but it also means that there are a lot of scales where the theory is sort of not anchored by direct observations. Likewise, we can do experiments with little dust particles, collide them together and stick. You're not going to collide together 2-kilometer-sized objects in the lab and determine whether they stick or break apart. Only in a science fiction movie, anyway.
Phil, sorry to ask another question, but can you explain what's going on in that animation on the left, on the upper right that you just had? It seems like you've centered a bunch of little simulations on some kind of grid points in a box, but then it also seems like things are colliding and becoming bigger. Is that because you're like running into you're simulating existing planetary systems into the future and they end up colliding?
Okay, so I probably shouldn't have showed this movie because it's actually got nothing whatsoever to do with any of that. In some ways it's better because this is actual real. This is based on real data. So these are planetary systems, actual planetary systems that were discovered by NASA's Kepler satellite through the transit method, and it's those planetary systems where there's more than one planet. So they're actually all to scale, and so they're just like. They're just little animations of how the planets are going around those stars. Yeah, each one's centered at a different point, so you can see them, and the sizes of the circles show the sizes of the planets and so forth, right? So mainly it's to demonstrate that Kepler found a ton of these systems, and it's also a pretty thing. If I've had the movie on, it even has some if I had the sound on, it even has some soundtrack, but we don't have that. So there's a lot of these are the close-in planetary systems that I said were like super common. Okay, so let's turn then to these sort of questions of things we don't know or things where there's big uncertainty. And so the first questions, I'm going to have 3 of these questions. So the first one is sort of I'm going to spend most of the time on, and then I'm going to say more briefly 2 others. The first question is, when do planets form? How quickly does this process I've described play out in real systems? And the old answer, where old is maybe only 10 years old, was that this is a fairly slow process. Okay, so in the left-hand side here, you're seeing a simulation of the formation of the terrestrial planets. So it's distance from the star on the x-axis, eccentricity on the y-axis, and you're seeing a purely gravitational simulation of initially fairly small bodies being scattered in their orbits until they collide with each other, growing into bigger things, and then continuing to do so. And the colors are actually showing how water gets mixed in that system with that story of the asteroid belt I gave before. And it's just stopped here at 200 million years. And you can see that you formed there 3 planets, roughly speaking, where Venus, Earth, and Mars are, with pretty low eccentricity. And then there's a few dots further out that are sort of something like the asteroid belt. Okay? And it's taken quite a long time. And that is actually sort of consistent with what we think we know about the moon, because we think the moon formed in one of the last or the last of these giant impacts on the Earth. And there's efforts to date that from looking at lunar rocks, which maybe put that time at like 50 or 100 million years after sort of the Earth got started forming. So that's a long time. It's longer than that 3 or 5 million years gas disk lifetime I was talking about. Now, if you want to form giant planets, you've got to do 2 things. First of all, you've got to build that core of a few Earth masses. That's going to take some time. And then the gas has got to flow in onto the planet as well and contract to form Jupiter. And in order for the gas to flow in, it has to lose energy, it has to radiate energy away. And if the gas is full of dust, it's quite opaque. So it takes time for that radiation to flow out and for the planet to get built. So the standard answer is that you can form Jupiter in a few million years where Jupiter is. But if you went further out in the planetary system to tens of astronomical units, tens of Earth-Sun distances, then the timescale for building a planet like Jupiter would be, effectively infinite, right? It just wouldn't happen. And as we looked at that, a group of us looked at it recently, trying to do better radiation hydrodynamics simulations of basically how the energy gets out of those planets. And the bottom line was actually we found a result that was pretty consistent with what people found back in the 90s. It really takes, by standard processes, quite a long time to build a planet like Jupiter. So that's the expectation. But observations of disks in the last 5 years, 10 years have really challenged that view and that theory. And what you have here is just a compilation of images of protoplanetary disks. So this comes actually from Quantum magazine from a little while ago. Some of them are taken in radio wavelengths, and some are in optical or near infrared wavelengths. But the point just to notice is that these disks don't seem to have a sort of smooth distribution of emission. A lot of them have rings of emission, and then some of them have other structures that look more like spirals. So if we can see here, let's see, here we go. So yeah, so this is a classic example. This is a case where you see multiple rings of emission around the star. And then here's a case where you see the structure is more in the form of spirals. And then there's some other examples of kinds of structure you see there as well. So most of disks that we observe closely enough show this kind of substructure. So it's common: rings, spirals, crescents. So that's what we see. Why is that a puzzle? Well, in one way, it's really good, because it's long been known that one way to make structures like that is to have planets in the disk, and the gravity of the planets perturbs the gas, and then the perturbed gas manages to sort of concentrate dust in some kind of observable substructure in the disk. So I've written a textbook on planet formation. So I was writing this like 15 years ago, and the first edition had like a simulation of that process. And you see the planet there has made a dark gap. It's carved out a gap around its orbit, and you see a sort of spiral wake propagating out into the disk. And we weren't the first to do those kind of simulations. Those simulations were being done even in the 1980s. Right? So it's a really old result. Okay, so you step forward, 10 years. We see that in direct observations of disks. The second edition has one of those actual data on the cover. It looks pretty much the same thing. So that sounds great. It's a sort of example of theory that appears to have been confirmed by observation. But there's a but, which is that the observed rings are, in many cases, a long way from the star. So they're like 50 or 100 times the Earth-Sun distance away. And moreover, they're seen in pretty much every disk we look at closely enough, including disks where the star seems to be really young, so less than 1 million years old. It's hard to date young stars, but you can make some efforts to do that. So in the sort of standard old theory, planets should not form that fast, nor should they form that far from the star. So if, in fact, those rings are being caused by planets, if you like, we've confirmed the aspect of how planets interact with their gas disks, so that's good, but we have a problem in understanding how we actually form those planets in the first place. So basically, we don't know what's going on here, right? So this is a big open question. A lot of people are working on that from both a theory and an observational point of view. But there are various possibilities. So I'll just skip through the possibilities. So the first possibility is that when I said, well, it looks like we would have planets and planets would be doing that, maybe actually that's not right at all. Maybe it's the case that a protoplanetary disk can spontaneously develop rings in its structure, even if there are no planets there at all, okay? And I don't want to go into that particular possibility anymore today. There was actually an FRF at CCA a few years ago who worked quite extensively on that possibility. There are various magnetohydrodynamic possibilities for how that might work, right? And people argue about how plausible those are or not, but it's a possibility. But most people, for various reasons, prefer the idea that they're planets, and there are actually a few cases where the planetary interpretation has been confirmed. So there's a little bit of reason for that. So there are two other ways in which it might work. So one possibility is that we abandon the solar system sort of idea that growth starts at small things and just kind of steps up consecutively to bigger and bigger objects. So we go from dust to centimeters to planetesimals, which are kilometer size, and then those keep colliding in a sort of pairwise fashion. So the basic idea is that instead of that, we make some biggish objects, and then they grow really quickly by sweeping up a lot of the small stuff, which is sort of left over. So if like the protoplanets sort of grow from like a hailstones or something like that in the protoplanetary disk. So there's a plot here from a very recent paper by Vlad Lyra's group in New Mexico discussing how that works. And I'll say a little more about that in a minute. And then there's a third possibility, which is actually maybe the most exciting, which is, maybe this data is pushing us towards actually a different mode of planet formation that could take place in really young disks, but would not be able to take place in the older disks that were the previous focus of planet formation theory. And this is an idea which we're looking at in sort of various dimensions. here at the moment. But let me step back to the previous possibility, the idea that it's pebbles that are sort of saving the day here. And if we go back to sort of the first part of that cartoon I showed earlier, I sort of left out an important part. I said we go from microns to millimeters by things colliding and sticking, and then we make planetesimals that are kilometers in size. And I didn't say, well, how does that step work? Okay, and that step has for a long time been a puzzle. So if I'd been giving this talk 10 years ago, maybe, I would probably have made that step as being like the biggest unknown in planet formation theory. But we have made some progress there. And we think we know a mechanism that can do it. But it's quite a subtle and complicated mechanism that it actually relies very extensively on numerical simulations to try and understand the details. But the basic idea is that if you have gas and then you have solid particles, so centimeter-sized objects, let's say pebbles, which are interacting aerodynamically through drag forces with that gas, it turns out there's a linear instability of that coupled system. And in this context, it's called the streaming instability. There are also many other streaming instabilities in astronomy, but this is a streaming instability. And the nonlinear evolution of that is to form dense clumps of solid material, dense clumps of pebbles. And so the basic idea is that this instability forms dense clumps of pebbles, and those clumps become so dense that they collapse under their own gravity to form the planetesimals. So it's sort of quite distinct from how growth occurs at either smaller or larger scales, because it's really a collective phenomenon, right? So it's not individual things colliding in pairs, it's a whole clump of stuff that happens to collapse down to form a planetesimal. So we and many others have done work on that, simulations on that. I was showing some work from Ocean Lee and Andrew Udin. It's a complicated story, but basically if you can have a protoplanetary disk and have enough mass of pebbles of the right size at the right place, the instability can be triggered, and then it will work as I've described. Clumps will form, gravity will bring things down, and you'll make the planetesimals. And the movie you sort of saw there, maybe for those who've sort of seen pictures of cosmology simulations of galaxies forming, it looks a little bit the same, right? And of course the reason is that it's gravity, which is basically here drawing together a collisionless fluid, which here it's pebbles, and galaxies it would be dark matter, and that's kind of driving this kind of structure formation. Okay, so that's maybe how it works, and it's interesting from this point of view of how quickly we can form planets, because when we do simulations of this, one of the things we agree on is that the mass function of the planetesimals you form is top heavy. So if you take a certain amount of mass, most of that mass ends up in a small number of the largest objects. There's also like a zillion small objects. So by number, the small objects win hugely, but most of the mass ends up in the big things. And for reasonable parameters, the big things can actually be quite big. So I said planetesimals were like kilometer sizes. That's like an old-fashioned view. If they form by this mechanism, they may be hundreds of kilometers in size. So then really they're like the largest asteroids we see in the asteroid belt, or very large comets, extremely large comets that we basically very rarely see in the inner solar system. So that's what we think. The simulations of this process are very challenging. Basically, you've got two fluids, they're interacting with each other. So, asking how well converged that is, do we understand how it works, particularly for a distribution of particle sizes, is hard. But there's some promising agreement with things we see in the outer solar system. So that object that was flown by Arrokoff looks like perhaps it was made by this kind of process. So that may be what's going on. We think that's maybe what's going on. And that then sort of allows us to make perhaps a story, maybe a slightly challenging one to make working details for how you can make planets quickly, far from the start. And the idea would be you form the pebbles. We know that part is fast. You trigger this streaming instability, and you make a small number of very big planetesimals, or sort of minor planets. And then the minor planets accrete a lot of the remaining pebbles, and then they grow very quickly. Okay, and that escapes the bottlenecks that would otherwise be present in sort of the solar system mode of planet formation. So that's a possibility. Maybe it's a plausible possibility. A big unknown is that we don't really know what sets the balance between the planetesimals and the pebbles. So in one of our simulations, which are like little boxes of gas and dust, once you start forming those planetesimals, actually most of the mass just ends up in the planetesimals, right? So then you've got no pebbles left over. We know that's not true because we see pebbles in protoplanetary disks, so we know they survive somehow, but we haven't really got a good understanding of how that works. Okay, so that's one possibility. Another possibility is maybe there's a new mode of planet formation. And the sort of possibility here is that if we go early enough, the disks around young stars would be, we think, more massive than the 10th of the stellar mass that I was talking about earlier. They might be half the stellar mass. Sufficiently early time, there wouldn't have been a star at all, and so all of the material would have been sort of infalling in some way. So those disks that would be massive would be self-gravitating in the sense that their dynamics would be controlled also not just by the gravity of the star, but also by the gravity of the disk gas itself. And so that is the situation, we also see sort of in galaxies and works the same way pretty much. You end up forming spiral arms in the disk. This is a simulation. You form spiral arms. Maybe again, that's what's being seen in some of those images of young protoplanetary disks. And then in those environments, things can work a little bit different. And we've sort of explored some aspects of that, or are exploring some aspects of that now. So Wenry Zhu here, who's FRF at CCA, has been looking at how the pebbles grow in that scenario. And we find that you can grow somewhat larger pebbles, actually quite a lot larger pebbles, in sort of the dense environments of self-gravitating disks compared to what's assumed at a later stage. So instead of maybe stalling at millimeter sizes, maybe you can grow 10 or 100 times larger than that, okay? And then if you grow those larger pebbles, they may collect together in the spiral arms in such a way that they can gravitationally collapse in the spiral arms to form objects directly. So Cristiano Longarini, who visited here for a while in the spring, last spring, has done simulations of that process. And again, with the right parameters, the right assumptions, the spiral arms can collect together material that could collapse and directly form planets very quickly. So do those scenarios work? There's a lot of uncertainties in really piecing together whether the conditions and whether the physics really works well enough for that to happen, and how that kind of model would fare compared to those other possibilities that I was describing before. But it's something we're interested in and we're hoping to work more on. Okay, so let me now turn more briefly to the other questions. So I was sort of talking about what happens early on. What about if we think about what happens really late and what determines the final shape of a planetary system? So the question here is the final shape of a planetary system sort of controlled at the point where the planetary system was first formed? So that's maybe at a few million years, or does it continue to evolve for a much longer period? And if we go back to when exoplanets were first discovered, the first exoplanet to be discovered was a Jupiter sort of type planet in a few-day orbit around a star, so-called hot Jupiter. And an immediate interpretation of that was that that planet could not have formed where it was now seen. It formed much further out, and then by interacting with the gas, with the disk of gas and dust it formed from, it migrated inwards and then ended up stalled close to the star. And that was, an attractive and an immediate hypothesis, because there was work even dating back to 1980 discussing exactly how that process might take place, how a planet might lose angular momentum to its disk, move towards the star on a relatively short timescale. So gas disk migration was considered to be a good way of forming the hot Jupiters. Now, the next few planets that were found back in the sort of mid-90s, many of those were further out, and they had quite eccentric orbits, sometimes very eccentric orbits. And again, an immediate explanation for that was sort of put forward. Perhaps what happens is that these planetary systems were initially, the planets were quite closely packed together, so they were unstable on a long period. They had close encounters, they had some collisions, some of the planets maybe got ejected, and then the result was that the survivors ended up with eccentric orbits. And you can do very simple numerical experiments of that kind of process, where you just take a few Jupiter mass planets, put them on circular orbits, but close enough to be unstable, let it evolve for a few million or a few billion years, becomes unstable, that happens, and you get a distribution of eccentricities that actually matches very well what is seen. So it seemed like the whole matter was done and dusted. Theory had been found that would explain the observations. However, subsequent observations have suggested a much more complex situation. And the key one, perhaps, is that at some point it was realized that you could measure the inclination of exoplanet orbits with respect to the equator of the star as defined by the stellar spin. So in the solar system, the planets orbit pretty much in the plane of the sun's equator. There's about 7 degrees misalignment in the solar system, right? So it's pretty much, in the plane as you would expect. The sun is rotating this way, the planets are in a disk around the sun. But in a fraction of these hot Jupiter systems, these exoplanet hot Jupiter systems, the planets do not lie in the equator. They can be polar orbiting, or they can even be tipped over and retrograde, okay? And that's clearly a really puzzling thing. It's like a really amazing thing to find, okay? And again, there was like some theory that had been developed in the 60s to think about asteroids in the solar system that gave an immediate possible explanation for that. If you have a star that's part of a binary star system, and the binary star system is misaligned with respect to the planetary system, then there can be an instability which causes the orbit of the planet to become both very eccentric and very inclined, and the sort of oscillations of that process. And so that's a different way of making hot Jupiters. Maybe you form the Jupiters far out, they have these oscillations, they become super eccentric. At some point, they closely approach their star, and then tides bring the orbit down and circularize it at small scales. And it's a completely different way of making hot Jupiters, which can, however, make those inclined systems. And then, there were other puzzles that were later found for lower mass planets, which were discovered by the Kepler satellite. So those observations and then, subsequent theoretical work have, to some degree, just muddied the waters in finding many possible physical processes that could plausibly be playing a role in these kind of observations. And here's just a list of them, which I don't really want to go through. But basically, the gas disk migration has been found to be much more complicated than was assumed in the 1980s. That's obviously not a surprise, because the 1980s calculations were pencil and paper, and now people are doing simulations. And then the purely gravitational dynamics is also extremely rich. And so there are many ways in which it can work, depending on exactly the configuration of the planetary system or the stellar binary system in which you start. So, a lot of fascinating work has been done on this, but the basic question, which you might hope to pose, remains open. What is really causing the observed systems that we see? Presumably, some of these processes are more important than others. They could all work at some level, but presumably some of them are dominant. Which are those? And, in the early solar system, which of those, if any, worked in the solar system? And, more than 25 years after the discovery of those first exoplanets, those basic questions actually still remain open. There is progress here, so I don't want to make this on a negative note. There's computational progress. So I would say, in the last few years, really for the first time, we've gotten to the point where we can simulate these gas processes with pretty good fidelity, right? So we can go beyond just exploratory experiments to calculations that we think are yielding the correct answer for how quickly planets should migrate and move around in the gas disk due to these processes. And we have people here doing those calculations. And then we're also trying to understand how to do the in-body dynamics, the gravitational dynamics, approximately but quickly. So we can already do that with very high fidelity with numerical integrations, but they take a long time. And so we're developing some machine learning approaches that can give approximate answers that we think are good enough to then embed in larger calculations of how planetary systems evolve. And there are also promising observational directions, which the data group, especially at CCA, is looking at, trying to find, if you like, some of the missing links, perhaps, between planets that start far out and end up close in. At some point, they must have been sort of halfway. Those would be so-called warm Jupiters. And if we can find a sample of those, maybe that tells us how the migration process takes place. And there's some other directions that we can also take in that way. Okay, so let me then just finish off with a couple of minutes on a final topic, which is a different kind of astronomical object, a circumplanetary disk. So far I've been talking about disks around stars and forming planets within those disks. However, we can also have disks around the planets themselves, at least if they're giant planets like Jupiter. And in those disks, we would be interested in the formation of moons or satellites rather than planets. And the existence of such disks has been known about for a long time, or at least inferred for a long time, because if you look at the Galilean satellites of Jupiter, they all lie in a plane. And Kant and probably many other people, more than a century ago, observed it looks like a miniature solar system, and therefore it probably formed in the same way as the solar system from a disk. And in a more modern way, we think what happens is that the giant planet opens a gap in the disk, but then as gas continues to flow across the gap towards the planet, it circularizes in a little circumplanetary disk around the planet. So that's our theory, and what's been very exciting last couple of years is that there's been the first detections of those systems. So here's another ALMA image. So there's now a radio image here. So here you have a star, and here you have a disk, which is, you can just see the ring here, and then you see this dot at the 3 o'clock position. That's the location of an extrasolar planet, in this case, a young extrasolar planet in that disk. And if you look at this closely enough, that dot is actually resolved. It's not just a point, it has an actual spatial extent, and that is the circumplanetary material, we think, around that planet. So we've sort of found one, or observers have found one of those systems for the first time. So theoretically, that's very exciting because quite basic questions about circumplanetary disks are completely open. So on the small scales, we don't know how the gas in that circumplanetary disk ends up joining the planet and making it, grow larger. So one possibility is that the planet has a magnetic field, and the gas sort of flows along the magnetic field and hits the planet in a shock, in a hot spot. That's what we think happens for young stars. Another possibility is that the planet magnetic field is not as strong, and the gas sort of flows into the equator and forms a belt, if you like, around the equator of the planet. And which of those is the right answer has a lot of implications for how fast planets spin, how we might detect them, and whether planets might launch jets, small jets perhaps, like that star that was launching a jet I showed in the image at the start. On the larger scale, we don't know whether circumplanetary disks are sort of isolated entities being fed with gas that then just feeds on into the planet, or whether some of that gas actually manages to escape back into the protoplanetary disk in a sort of circulation flow. So that's another question we've been looking at, and we found some evidence that maybe under some circumstances it can be that escaping mode rather than just the inflowing mode. And that has actually a lot of implications for how easily you might be able to form moons within those circumplanetary disks. And that's something we've been looking at different numerical approaches in particular to try to understand. And then finally, sort of most speculatively, we don't even know for sure that these disks are coplanar with the overall protoplanetary disk. So there's some instabilities which could actually cause those circumplanetary disks to tilt out of the plane and ultimately maybe reorient the planetary spin. So you're looking here at some simulations. These are grid-based simulations where the overall plane is the plane of the protoplanetary disk, and this instability is operating and tilting the circumplanetary disk until it reaches 40, 50 degrees off the equator. So that would be a wild possibility that you have this strange dynamics taking place in these disks. So it's a very rich subject. We're looking at multiple theoretical avenues to it, but the most exciting thing is that we expect a lot more observations of this in the near future. So let me just finish up there. What we don't know about planet formation is, I think lots of things, but I don't want to finish on a negative note. I think one thing I would emphasize is, the amazing observational progress. If you really think we found thousands of exoplanets, we can really observe circumplanetary disks around young exoplanets around these distant stars. That's really amazing progress that we've been able to do that. And it's driving a host of both new theoretical ideas. That sort of pebble accretion scenario I discussed, was only discussed first in about 2010, so it's a pretty recent thing. And new computational tools, which of course is where here at Flatiron we come in. And at CCA, we're interested both in that sort of computational aspect on the theory, and also on the data side of how you can actually make the comparison between the observations and the theory. So I'll stop there and take any questions.
Okay, great. So if we have questions for Phil, and then I'm assuming that the AV crowd can let us know if anything comes in over Zoom.
Great talk, Phil. This is very exciting. I wanted to know kind of a big picture question of when you listed all those possible putative dynamical processes earlier, I wonder whether some of the observables, say misaligned hot Jupiters, perhaps they're, that misaligned hot Jupiters can probe, you know, whether and how fast secular secular migration happens, secular dynamical processes happen. But when you superimpose multiple putative dynamical processes, how do you think observables can deal with that?
Yes, I mean, I think that's it's a great question, and it sort of cuts to the heart of why, despite all this data, the questions still remain open, right? I think there's some hope in that there are some signatures that are fairly specific, right? So in particular, some dynamical processes have a sort of natural timescale that is relatively short. There are some which are instead billions of years, right? So secular chaos is the main example of that, which takes a really long time. So if we could really observe how the typical planetary system evolves between young and old stars, that would say something about at least whether, say, secular chaos works, right? Likewise, if you look at pairs of resonant planets, that says something mostly about gas disk migration because it requires some dissipation. So there are some sort of key systems there, right? And so my feeling is that the key is to develop, an understanding of the data samples that is good enough to understand, what the selection biases are in the data, and then, really focus in on those special systems, not really on the, the whole population, where, as you say, everything gets mixed up and it's kind of hard to see what's going on.
Yeah, thanks for this great talk. I was wondering about you showed the simulation of the eccentricity versus periods that formed in the end 3 planets. I assume that one was done with a 1 solar mass in the center. How would that be drastically different with a more massive star? Because 200 million years stars to be the lifetime of a 5 solar mass star. So do we see any configuration with Venus, Earth, Mars around a more massive star that?
Yeah. So I guess the dynamics itself will have some sort of trivial scaling, right? Because up to the collisional cross section, it's going to be just it's going to just have a simple scaling. The main issues with more massive stars are to do with the properties of the disk, because once you get to those more massive stars, then the high energy radiation from the star is going to ionize the disk. So those are probably going to be poor environments for sort of many of these things because of that. So I think that's going to be the biggest bottleneck. And observationally, we don't really have much evidence once you go to significantly more massive stars, right? You can go a little bit more massive, but not much more. Rachel.
Really nice talk, Phil. Thank you. So it seems like you could constrain these different channels for planet formation from the observations of the beautiful disks from ALMA, and obviously to some extent you were using that as motivation to consider these new channels. So what are the limitations for directly constraining sort of the mass function of these clumps? Is it you need more sophisticated simulations, you need better synthetic observations, you need better observations? What's limiting you there from just being able to say it's got to be this one?
Yeah. So I think so some of it is just scales and optical depth, right? So a lot is really enshrouded, and even in principle you can't really see.
Right.
I mean, I think the aspect I didn't talk about, which is very powerful and is sort of still developing a lot, is measuring the velocity field from molecular lines, also with ALMA in the radio, right? And so that does constrain a lot of these things. And in particular, if we really had very good kinematic data on those disks with rings, we would be able to see whether there are planets there or not, right? The difficulty is just that that requires much deeper observations. It may or may not be possible eventually with ALMA, but it hasn't been possible very much to date, right?
But it would be possible with just longer integration time.
Yeah, and so that's one direction. Another direction, which you know about, of course, is if we could look at longer wavelengths, more like centimeter wavelength radio, then of course that would probe larger particles, and that would, again, probe a different region of parameter space, and that's of course the NGVLA motivation for those who know about that.
Great, thank you very much.
Thank you very much for the very instructive talk. I have a question about the iron core of the Earth, which we supposed to have because of the magnetic field. So is it known how that formed? Is this simply because iron is one of the heaviest elements among the abundant ones, or why do we have so much iron in the core?
Yeah, so that's basically the supposed so the question is what about the iron core of the Earth? How do you form an iron core of a planet, and what does that say? So yeah, I think the iron core of the Earth is basically consistent with the amount of iron we would sort of expect to have in the Earth-like material, and then it's sinking to the core during the early phases of the evolution. Mercury has a much higher density, and there are some exoplanets known that also have very high densities. So those pose more of a challenge because maybe those are largely iron objects, and so then there's the question, well, where's the rest of the stuff that should be there? And so in the case of Mercury, it's long been suggested maybe there was a giant impact that blew off all the non-iron stuff, and maybe there are more massive planets in exoplanet systems that actually have that same general property. So those are kind of interesting systems for that purpose.
We have time for like one, maybe two more questions.
So that is basically, so the first answer is that it's a question about chemistry, and I know nothing about chemistry. So the first answer is I don't know. Okay, but basically there is fractionation processes can take place, particularly in the atmospheres of the disks. And so depending on where you are away from the star, you can change that ratio. That's how I understand it. And it's actually a large variation. So it's a factor of 3 or something like that. And it's more complicated than I told you, because actually there are some comets. There's like a subclass of comets that is more like the Earth's oceans. So there's still in fact some debate about it. But yeah, but basically there are pretty distinct variations that we see between the asteroid reservoir, which we see in meteorites. It's meteorites that tell us that, and then the comets, which of course is all indirect, remote observations.
Okay, thank you.
Last question.
We'll talk. So I remember being an undergraduate astronomy student and really learning about this meter-sized gap as this big mystery in planet formation. With the advances of streaming instabilities and things like that, how accepted is streaming instability as an answer to that, and how much is this still, one of the big mysteries of planet formation versus how solved is it?
Yeah, so I think the streaming instability gives a way of doing it, right? There are still questions about how easy it is to get into the regime where the streaming instability works. Okay, and so there's sort of two parts to it. So I said it was a linear instability, and that's true. And so the instability itself is very generic and robust. So there will be a streaming instability. But having the streaming instability produce the dense clumps that form the planetesimals is, a second question. And in particular, there's some recent discussion about if you have a size distribution of particles, which you will have, right? So there'll be some big ones, some small ones. Depending on that size distribution, even the linear growth rate of the instability can be very different. It can be like very strongly suppressed. So in that sense, it's still an open area of research, not so much whether the streaming instability works, but whether it really does the job of making planetesimals. And it might be, that it only works in sort of particular places in the planetary system. So there might be special places where it works and other places where it doesn't work. And so there's a lot of sort of open questions there. But it's, I think, still considered substantially more likely than the alternative, which would just be ongoing collisional growth, which has this meter barrier you were describing.